Good day, everyone. My name is Denis Shushin. I would like to thank the organizers of the COM 2024 conference and my co-author Najenda Tripathi from Rio Tinto for an opportunity to present a part of the current project. The topic of the presentation is the link between slag chemistry and arsenic flows in primary copper smelting. Several recent publications inspired me for this talk. The first provides a detailed material balance for the flash smelting furnace, including the dust recirculation and slag concentrate recirculation for the operation in China. The second provides in-depth analysis of mineralogy and composition of flue dusts. It was performed by researchers from Central South University and Al Alto University. In the latter study, samples from two copper plants were collected. One used a flash furnace, another a bottom-blown smelting furnace. These represent two main types of modern smelting technology, suspended and bus smelting. In both cases, waste heat boiler and electrostatic precipitator units were used for the gas cleaning, with the samples collected from these units. Some quotes from this study are: the off-gas is treated in waste heat boiler, then ESP, leaving an essentially solids-free off-gas stream for acid making. In industrial operations, the flue dusts are usually recirculated back to the feed mixture of the smelting. Then arsenic content in the flue dust is accumulated, affecting the quality of anode copper. Then the dust is treated separately. The focus of these studies was on the smelting stage. What was of interest to us is to perform thermodynamic calculations using FactSage software for high temperature units in these flow sheets, including converting and fire refining stages. Also, we tried to collect and use the information about the non-thermodynamic factors in these processes. Something what was not very clear from both studies was how much arsenic bypassed the gas cleaning system and proceeded to the acid making process. In our simulation, we assumed the complete dust recirculation until arsenic levels achieve steady-state conditions before the dust bleeding is necessary. In Copper 2022 conference in Chile, we provided the review of experimental information for the distribution of arsenic between slag metal, and matte metal phases. These data have been assessed together with literature for other types of distribution data and thermodynamic properties. Together, these were used to develop a self-consistent thermodynamic database for FactSage software. The current database covers 20 elements. FactSage itself is not very suitable for process simulations due to the inconvenient interface for the manipulations with streams. So we developed an Excel macro code which allows us working with streams in Excel while performing complex multi-component, multi-phase calculations in FactSage. This method is definitely faster than manual calculations in FactSage, but slower compared to the dedicated flowsheeting software such as HSC or SysCAD. Still, it provides the full power of thermodynamics without the need to set up extents of the reactions. Let's talk about using thermodynamic calculations for process units. First, each process unit can be represented by several equilibrium calculations. The number of equilibrium calculations depends on the level of depth of analysis and availability of detailed information inside different zones of the reactor. For example, in case of smelting, we can use an equilibrium calculation for the incoming feed consisting of concentrate, flux, air, and oxygen, and fuel as well, if necessary. The products are gas, slag plus solid, matte or metal. To find the energy balance, an extra calculation is made to get the enthalpies of the incoming streams. Non-thermodynamic factors are introduced to represent inefficiencies in the reactor, or the fact that the portion of input can bypass the reaction zone. The commonly used factors are oxygen efficiency, volatile fuel, and mechanical dust carryover, as well as non-equilibrium evaporation of arsenic. The settling zone can be included in the model if additional reactions are expected there. Entrainment coefficients, which are sometimes called suspension indices, can also be introduced here. The gas and other carryover streams are processed in a condenser unit representing waste heat boiler and electrostatic precipitator. It operates at low temperature so that all volatile species form solid compounds combined in a condensed dust. The condensed dust is recirculated to the feed. Let's now compare cases 1 and 2. From the chemistry point of view, the main difference is converting slag system. In the case of flash converting, a calcium ferrite-based slag is commonly used, whereas in the case of bottom-blown converting, the current practice is to use the iron silicate-based slag. For the sake of comparison, the same concentrate compositions and throughputs were used on the dry basis. The concentrate has average amount of arsenic. The operating mud grade in case 2 is reported to be a bit higher compared to case 1, but a reported oxygen enrichment is a bit lower. An important difference is that much lower moisture content is required for the operation of flash smelting furnace in case 1. Concentrate drying requires capital investment and operating cost, which was outside of the scope of the present study. Also, the mechanical dust carryover, which is a non-thermodynamic factor, is higher in case 1, but the entrained mud droplets in the smelting slag is higher in case 2, which is mainly due to the presence of high amount of suspended spinel solids during the slag skimming. This will be discussed further. Other non-thermodynamic factors are treated to be approximately the same. So, what are the results for case 1? We have a flash furnace producing a 70% copper matte and a fayalite slag with iron to silica ratio of 1.4 at 1300 degrees Celsius in the reactor zone. This ensures solid-free slag in the settler zone. The amounts of air, oxygen blast, and flux are calculated to achieve these conditions. They also account for the small addition of coal fuel, which is required to achieve a combined energy balance for this furnace, estimated at 20 megawatt heat losses. In the gas cleaning system, a large amount of dust is collected, which is being recycled back to the feed. The slag, which is produced, is treated through the process of crushing and flotation, so some of the copper and arsenic is returned in the form of slag concentrate. Recovery of 75% for copper is assumed for the crushing flotation. At the converting stage, metallic copper is produced. The fluxing is done using calcium carbonate, forming a calcium ferrite-based slag system with high concentration of copper oxide with a 22% copper. This slag is not discarded but brought back to the smelter. The energy balance in the flash converting furnace is achieved assuming smaller heat loss due to the smaller scale and lower operating temperature compared to the flash smelting furnace. To simplify the model, the dust generated in the converter is recycled to the converter. The last stage is anode refining, which is achieved in 2 steps: further oxidation of sulfur and then reduction of the oxygen from blister copper using methane. Small heat loss and small generation of slag is predicted. The slag is sent to the converting stage. Dust Thus, there are only three output streams from the process. The first is the anode copper. The second is discard slag after flotation. And the last is clean off gas. The amount of metals, including arsenic, in the off gas is negligible. Let's see the results for case 2. At the smelting stage, we produce matte of 74 weight % copper, which requires a bit more air-oxygen blast compared to case 1, particularly because it has lower oxygen enrichment. The amount of silica flux is smaller because higher iron to silica ratio is targeted. Temperature is lower as well. Despite operating at lower oxygen enrichment and with high moisture in the feed, additional oxidation of iron sulfide, lower temperature, and lower amount of silica results in energy balance which is more exothermic. Even without coal fuel, energy balance adds up only with 26 megawatt of heat loss. It is likely that in practical operation some recycled products with low calorific value are being used, which are not accounted for in the present study. The produced slag is again treated in crushing flotation, bringing back slag concentrate. The slag entering slag crushing flotation has high amount of entrained matte due to the presence of large amount of suspended solid spinel. In the present study, it is assumed that copper is recovered with the same efficiency of 75% as in case 1. Further studies are needed to compare the behavior of case 1 and case 2 slags during crushing flotation. For the converting stage in case 1, it is reported that matte is fed into the furnace without granulation, continuously in a molten state. A different type of slag system is used. The produced slag has high concentration of copper of 23% as in case 1, but it is iron silicate-based slag. The slag is fed to the smelting stage. Blister copper is produced and then further refined. In theory, it is possible to conduct fire refining in the same vessel as converting, according to some recent publications. It is unclear, though, how logistics is organized if matte is fed continuously from the smelting stage, while anode copper is produced in several batches corresponding to converting, sulfur removal, and oxygen removal. Again, the output streams of the process are anode copper, discard slag, and clean off gas. To compare the slags at smelting stage, we calculated liquidus and lines of 15% solids in slag, as well as concentration of copper in slag for conditions of case 1 and case 2. Solid lines correspond to case 1, dashed lines to case 2. Circles show the operating conditions for case 1. Squares, operating conditions for case 2. First, we can see that operating conditions are above liquidus for case 1, even if the settling temperature for slags is somewhat lower compared to the reaction zone. This results in solid-free slags. In case 2, the slags are deep below spinel liquidus, which is confirmed by electron microscope images of plant samples. Chemical solubility of copper is only 0.6–0.8 weight %, and higher observed values in plant samples are due to the entrainment of matte. Here, we can see the difference in slag liquidus at the converting stage for cases 1 and 2. On the left, we see that for calcium ferrite-based slags, liquid slag region exists even at temperatures below 1200 degrees Celsius. But for the iron silicate-based slag, there is a risk of complete solidification at temperature below 1225. The viscosities of these slags are not shown here, but low values are expected for the slags on the left. Still, it is not that crucial for copper losses because these slags are sent back to the smelting stage. So from the point of view of liquidus, the converting operation at 1250 is possible for both types of slag systems. Let's now have a look at the distribution coefficients of arsenic for the conditions of smelting and converting. For the regime of complete dust recirculation, it is these values that will determine the final partitioning of arsenic between the anode copper and discarded slag. For the smelting stage, fayalite-based slags are used in both case 1 and case 2. There is a small difference in temperature of operation and effective PSO2 for the slag-matte interface. It is generally accepted that higher PSO2 values are expected for the flash smelting conditions, which causes somewhat higher distribution coefficient of arsenic. The simulated results can be compared with green lines and symbols showing laboratory experiments and calculations at the conditions of these experiments. Red lines and symbols are for slag-matte equilibrium with calcium ferrite slag, which are important for theoretical development of the thermodynamic model, but do not correspond to smelting operations at any copper plant. The diagram on the right shows predictions for copper converting conditions. Here, the use of calcium ferrite slags in case 1 gives a distribution coefficient which is 1 order of magnitude higher than in case 2, where iron silicate-based slag is used. This will have the most noticeable impact on the final partitioning of arsenic at steady-state conditions. This slide shows the partitioning of arsenic calculated in the present study. We can see that 0.69 tons per hour of arsenic enters the process with the concentrate, but much higher amount is being recirculated in the form of smelter dust, slag concentrate, and converter slag. Even though the mass flow of arsenic in the converter slag is relatively small, some arsenic is sent back from blister copper. Also, more slag with higher concentrations of arsenic is produced at the smelting stage of case 1, resulting in higher partitioning to the discarded slag. Thus, the predicted concentration of arsenic in anode copper is lower in case 1 compared to case 2. One should be careful about the absolute values, since there are many assumptions in the model and the model is still a much simplified representation of reality. But qualitatively, the conditions about case 1 and case 2 are meaningful. Also, it must be mentioned that very low concentrations of arsenic in anode copper create problems at electrorefining stage, so that sometimes arsenic-containing materials are even added to stay within the recommended concentration range and molar range with respect to antimony and bismuth. In addition to arsenic, the partitioning of all elements have been produced in this simulation. The recovery of copper, silver, and gold is very close for cases 1 and 2 and can be considered the same within the accuracy of non-thermodynamic parameters. It is largely determined by the efficiency of the slag crushing and flotation stage, which is not very well studied quantitatively. Reasonably large difference is observed for lead, and it can also be explained by the difference in the distribution coefficients at the converting stage. Opposite to arsenic, calcium ferrite slags are worse than iron silicate slags for lead removal. So, to conclude, the work demonstrates material and energy balance calculations using FactSage plus Excel macro with a streams recirculation. Typical process conditions and non-thermodynamic parameters have been analyzed for two important copper production flowsheets. Advanced thermodynamic database used to predict the partitioning of all elements, requirements for air, oxygen and fluxes, percent solids in the slags, and energy balance. The use of calcium ferrite slags at the converting stage helps redirecting more arsenic back to the smelting stage. At the smelting stage, higher oxygen enrichment and higher effective PSO2 conditions observed in the settling zone of the flash smelter create more oxidizing conditions at the fixed mud grade, thus giving higher distribution coefficients of arsenic for slag mat compared to the bottom-blown smelter. These two factors provide lower concentration of arsenic in anode copper for flash smelter flash converter operation, reducing the need for dust bleeding, for example by leaching. There are some more points for discussions. For instance, additional outlet for arsenic through the acid making process was not included in the predictions. Including it in the model would not change the conclusions about the applications of calcium ferrite slags in converting, but will result in somewhat reduced partitioning of arsenic to discard slag and anode copper. Also, it is interesting to discuss if it is possible to use calcium ferrite slags in bottom-blown converters. The need for dust bleeding can also be reduced by implementing sodium-based slag systems at anode refining, which was originally proposed by Gerardo Alvera, Yamaguchi, and Pascal Coursol. I would like to thank the consortium of copper-producing companies for funding the fundamental experimental and thermodynamic work. The funds for this project and conference trip are provided by Rio Tinto Singapore. Here are the references used in the study.